battery up yet because that was one of my review ones. There was a couple of y'all that if this was the bus, you drew your batteries. Oh boy, ooh, it's a rough day. You drew your batteries like that and went through a master and connected it to a bus. And that would be backwards, just so you know. It sounds like a little thing, but if you really want to get a 4 for 4 on using your reference material and stuff like that, the small terminal on the back of a battery drawing is the negative. The large, wide one is the positive. So if you want to draw them correctly, let's see here, small, large. You want your batteries to go that way, so that the wide one is the positive terminal. Seems small, but you know, make sure we get that correct. The other thing is, especially on some of the ones, I think it was the Circuits Lab 8, you connected something, you connected the master relay, that's what it was. You connected the master relay back to the battery, but all your stuff out here that you said was just connected to ground, remember that's a wormhole, that's a teleporter, and it teleports to all the other ones, but if you don't connect your battery to ground, none of our electrons can teleport in or out of the battery. So you have to make sure, if you're going to draw those out somewhere like that, you got to make sure that you also connect the negative of the battery to ground.
Do you want our circuits to reflect ground going through the aircraft skin, or should we have our circuit with the wires going back to the battery?
Doesn't matter to me. Yeah, it doesn't matter to me. It shows the same thing because the reality is these don't necessarily even say that. Like, if I put a ground on the end, that might just mean I ran the wire back to the battery. It might mean I connected to aircraft skin. It can be a couple different things. That basically just says, hey, it did get grounded somewhere. Aircraft drawings. Yeah, if there's a wire back to the battery, you'd have a wire with a wire number on it. So there's that. But most of them don't. So you can do it either way. The main thing would be, if you show the ground out here, you absolutely have to put the ground here. And the reason for that is, when you go work on an airplane, hopefully we've taught you the first terminal you take off is the ground one. That way, if you bump your wrench on ground, it's not going to do anything, right? So if you just take the ground off the battery, well, I'll take it off there. There. We'll take the ground off the battery. You do not have a pressure difference between your system anywhere, right? Because the battery provides a pressure difference between here and here. So if it's not connected back to the battery, you can go touch positives to the frame of the aircraft all you want. Nothing's going to happen if your battery's not connected to ground. So it's really more of a principle idea and thought on the drawing that, hey, you got to absolutely make sure that's connected to ground to make sure that you're following me and tracking with me on that. So make sure on the drawings, if you draw ground out there, you draw ground over here. Everybody tracking with that one? Good. All right, I'm going to review these. Oh, one more thing. On your diagrams that, or not diagrams, your projects where you have to have a resistor in series with an LED. And the reason for that is, if you remember, an LED light is basically no resistance. Pretty close to it. Very little resistance, right? So if you push 12 volts through a basically no resistance, your amp draw is basically infinite. It's whatever the wires, it's going to burn stuff out. So you've got to put a resistor in series there. So if you had a 12 volt battery and you used a 12 ohm resistor, you would have 1 amp. Now it's kind of a waste of electricity to send the whole amp through an LED to light it up. So you're going to want more than a 12 ohm resistor, plus that would be 1 ohm times 1 amp. No wait, yeah, 1 amp. Well, that's not too bad. Watts, 12 times. It'd be 12 watts. A lot of those little resistors may or may not be able to handle 12 watts. So we're going to bump that up. If you did a 120 ohm resistor, now we've got 0.1 amps through that LED, right? So probably a 120 ohm resistor would work. We do know that you get up to like a 200 690 ohm resistors on there. So I grabbed one LED and I put it in series, and 690 ohm resistor on a 12 volt still lit up the LED I grabbed. So you could do some math. Let's do it for the fun of it. What would my amp draw through that LED resistor? So 12 volts divided by 690 ohms, 0.017, so we'll call it 0.02, 2/100ths of an amp. Not a lot of power, and the LED was nice and bright. So, you've got a range. I do have Anna ordering more resistors, so if you want to wait for like an exactly 400 ohm or something. But that's kind of the area we're in with those as we get to your project. We should have a whole tray showing up, so there'll be plenty to solder. But you've got a range that works. I would just say grab whatever LED you're using and use jumper wires. You know, be somewhere between, we like say 250 and 690 now. But test it on the bench before you put it in your project. Make sure the LEDs work. And you might even leave them on for 2, 3, 4 minutes. Make sure the resistor doesn't get too hot or burn up or something like that. Joe?
Yes, sir. So our lights are going to be wired in parallel with resistor before each one of them. What would happen if we were to, instead of put the resistor, 3 resistors, just put 1 resistor before the 3 parallel circuits?
Yeah, so, I'll just draw the big circle and put it on repeat. Resistor, diode, right, or LED. So this is how we normally prefer it, because it's going to look more like an airplane. What Job's saying is if you cut the resistor out of here, just make these the diodes out, and put the resistor back in here. Will it still work? Yeah, it should still work just fine. Where are we going to actually wire that in? Because these are out on the wing tips. So if we did it the original way with a resistor for each, it's closer to what we're going to see on aircraft. So I'm fine with either way. If we have enough resistors, it looks better to put one on each light bulb because it's closer to diagnosing like what an airplane would be if we start, let's say, shutting one of them off. We can hook the wire to one of them. So, but yeah, you can do it either way. Just trying to kind of keep it close to standard on an aircraft. All right, good question. All right, so with that said, our 2 systems that you're going to have, or 2 of several systems. One is our interior light, or I think they called it an instrument light. Usually we're going to want to put that as an incandescent bulb for similar reasons. You can do a resistor and an LED on that one, but if you've got 0.02 amps going through your LED, it's going to be kind of hard to control it here because there's not enough load to put much of a load on our transistor. So we would recommend on that one that you use, even if it's like a wingtip light or something like that out of the box, just a incandescent light is going to give you a little bit more amp draw here, which is going to make the adjustment work a little bit better. We've had people try to do it with LEDs before, and I mean, you should be able to get it with the correct resistor. Like if you put a resistor that's big enough and put a 10 ohm resistor in, you're back to it works, but it just works better if you do an actual light bulb. So recommendation there is do an actual light bulb, wingtip light, or just something about that size. You know, 40 watts, somewhere in that neighborhood works well. And I'm going to come back to that drawing in a minute. Similar situation for your landing light, not exactly the same, but similar. If you have an LED with very, very low amperage there, when we start doing our push to test lights, sometimes it can throw it a little bit funny. Shouldn't matter, but you know, it's in the neighborhood. So if you can do light bulbs for those, it's best. This one doesn't matter nearly as much as the instrument light does. The instrument light, it's nice to have an incandescent light in there just for a little more amperage. Otherwise, if you're going to do an LED here, I would target the lower end. So 200 ohm, maybe 120 ohm, somewhere down there a little lower for that resistor, just to get the amp draw just a little bit higher. Part of the reason for that is the connections in a lot of our push to tests, they're not the most amazing connections. So having a little bit higher amp draw through it sounds funny, but that said, we're gonna go through these two drawings a minute before we go into the PowerPoint for the ignition switch. If you're struggling to draw your wiring diagram out, I would draw your battery with your master and put a switch in there. There we go. Your battery with your master and a bus. And you might even put that on one page and throw a little voltmeter on it. This bus, you could kind of say, hey, that keeps going down for 20 foot into the ground. Or you could have a notebook, and every page of your notebook, you just start on the left side of the page with the bus over there, right? That's what they do in a lot of aircraft drawings, because they don't put the whole wiring diagram on one page. So while you're figuring it out, if it helps you simplify it, put this system on one page, draw it really big. Put this system on another page, draw it really big. And then once you get them all and it makes sense, then you can say, okay, I want to combine these all to one page for my final drawing for my 337, or even 2 pages. But that will help a lot of you guys simplify it and not get overwhelmed with the systems that we have going on there. You could technically turn in a 4-page schematic to me if you wanted to. Seems a little overkill, but you know, some airplanes do it. Mr. Ward?
When we get our, like, all our allocated clips fired up and stuff, do you want us to show that to you before we start wiring?
The wiring diagram?
No, just the alligator clips.
I don't necessarily need to see the alligator clips. A lot of you are showing me the wiring diagram. That's not a bad idea, because a lot of times I'll catch a little whoopsie in there.
Yeah.
So that's not a bad idea to show me the diagram, and I'll be like, yeah, that looks good. That might even be on the lab, but I don't think it is. A lot of times, what will help is before you try to wire the whole thing up with 60 alligator clips, is take this system, just wire it up on the bench from the battery. Take this system, wire it on the bench from the battery. Make sure that your individual components for your systems all work individually, and once you go, yeah, they all work individually, okay, now let's combine them and put them back in. It's practice, connecting, disconnecting, that's kind of the reason we're here. So I would recommend that highly, because you try to do them all at once, and all of a sudden you're like, where's that wire go? And then one of them's not working, and you're like, is it the whole system? So that's a recommendation too. All right, so we'll do I'm gonna say the easy one first, even though it's a transistor. Question?
Yeah, just about that circuit, when I was drawing it, so you're going to the potentiometer there, but that's gonna be a smaller wire than the stuff going through the transistor?
On your project, it doesn't really matter,
Yes,
but
but in theory, like, that circuit breaker is going for a bigger wire, but it's also going to the small wire, so if there was a short there, that would theoretically burn up the smaller wire first.
oh, I see what you're saying.
Would that normally be on the second circuit breaker, or no?
I don't think,
Like,
depends on
even
the
with a
aircraft
match-
and the system. Most of this is gonna happen in the cockpit where you got less than 3 foot of wire. So with less than 3 foot of wire, we're usually using pretty small gauge wire. So we're not running like a 28 gauge to this, we're just gonna kind of standardize and say, you know what, it's an 18 gauge wire, they don't weigh that much in the cockpit. So, I think generally speaking, you get down to a certain size wire, and they go, you know what, we're not going any smaller than that. If we check our chart, which might pop up later, it's 18 gauge, 5 amp, 10 amp. You go up to the next 20 gauge or 22 gauge, and the breaker you have to protect it gets so small that they're like, you know what, we're not saving that much weight anymore. If it was all the way back to the back of a 737, it might, but just in the cockpit, not so much. All right, so transistor, the idea is we got a tiny little potentiometer, right, that fits in our panel really well, and we want to be able to adjust the lights with it. We might have 6 to 8 lights connected to that thing, especially back in the old days when they were incandescent. There's a fair amount of amp draw there, and it would burn up our tiny little potentiometer in the dash. We don't want to put a honking big one. So we use a little potentiometer, you could say rheostat, to control a transistor that can now take the heat, take the amperage that gets mounted on that black plate, which is a heat sink, and a lot of times that'll be back behind the panel somewhere where it can reject the heat and it's got some room to do it instead of being right in with all your circuit breakers and stuff. So the easiest way to understand why this is working, it's back to general, we covered it a little bit, but let's start at half bright. So if we're a 12-volt system, this light is going to be doing its maximum lighting at 12 volts, right? But let's say I want to do half my wattage or half my brightness. If I was to put a point in here to put my voltmeter to, and I wanted to go from my voltmeter to ground and over to that point, if I'm half bright, I would be reading 6 volts there. Everybody following me? Yep. Because basically we're going to say, hey, I had, if I moved it over to here, I have 12 volts here, but I don't want the light bulb that bright. So I only want the light bulb to be 6 volts, which means this will be basically a 6-volt drop across it if I'm set to half bright. So what we know is the base on this, and it is a NPN on this particular one, the base has to be just slightly higher than the emitter for the voltage going through. And if we raise it more than just slightly, it'll allow more amperage to go through. So as we change this, the amperage changes, and once the amperage changes, the voltage essentially changes with it. So if you will trust me that at half bright we're at 6 volts there, that would mean that if I have my potentiometer set halfway, which is kind of where I'm pointing, that would be 6 volts, which visually looks right? Because if the pointer was pointing all the way up here, we'd have 12 volts. Down here, we'd have 0 volts to ground. So if I want 6 volts there, and you'd say, well, if you really want to split hairs and be technical, we're going to be, what, 6.47 or something like that? Because it's slightly higher. You've got the, I forget what they call it, the breakthrough voltage. Maybe breakthrough's not the right word. Avalanche, whatever they call that one.
Cascade.
Yes. There's a word when you're teaching general class that you study before class. And you say it's the amount of voltage that it takes to get the transistor to open. So, everybody good with that? At half power, that's where we'd be at. And if on this system, we'll throw in a number here, we'll say 6 ohms. So, if the light bulb, when it's light up, is 6 ohms, now, is the resistance going to slightly change when it's half bright versus full bright because of the heat of it? Well, maybe. We're going to ignore that for now to simplify it, but it's not going to change too much. So if it's 6 ohms at 6 volts, we're going to have 1 amp currently where we're at right there, right? So what if we want to say, hey, I want to go 3/4 bright. I turn this guy up to 3/4 of my voltage now. So we'll say 9 volts on my potentiometer. That thing's saying, hey, you got a potential to point at anywhere from 0 volts to 12 volts. So I go to 9 volts here. That means I'm putting 9 volts here. That means my output is now going to be, well, technically 8.6 something or whatever, right? Slightly smaller. Now I'm doing 8-point-some volts. If I divide 8 by 6, I'm going to be at 1 point, I don't know, I didn't do the math, 1.2 amps. I got more amperage going through there. And more voltage. So you'll see the wattage also changed. The first time we were at 6 watts. Now we're at 1.2 times 8, which is 18 watts. So there's a little bit of a funny thing where you go, well, technically, Case, the closer you get to 12 volts, we are on a parabola. So if I set it to 6 volts, I'm actually not going to be half my light output. I'm just going to be half my voltage, because watts are going to be your light output. So when you say half power, you know, there's that. But that's really all the deeper we got to go. If I was to say, I don't want that light bulb on, if I spin my needle all the way down to 0 volts, I just pointed at ground here, so I put 0 volts here, I'm not any higher than the output, right? So it's going to close that, and we'll have 0 volts, and now my light bulb's not lit up. So whatever I set that at, basically my output's going to be slightly lower than that. That's how the gate works for the transistor. So, does that help everybody kind of visually be like, oh, okay, yep, I get it, that's why we're wiring it that way. Okay, so that's that one. Kind of fun. One of those things where could have gone deeper in general, but we save a few things. We might even save one more for power plant where with transistors, but we'll see.
So I guess I was struggling to understand how many amps are we putting through our potentiometer? Because it's in parallel, right?
Very few.
Right. I guess I'm just not understanding how we don't constantly overamp.
Yeah, so if you take a ohm meter and go from here to, let's see, what is going to set the amperage through there? Even if it's turned all the way up, it's not so much, it's just not. I can't recall why it's little, but it's not. We don't, the point of them is we set them low so there's not that much going through. I think it's that relationship as we get closer and closer to 12 volts, it's easier and easier for the flow to go through here. And if the flow is easy to go through here, it's gonna say, why do I wanna go through there when I can just go through this? So it's back to, we got that balance of the less and less resistance I point my little needle at, the less resistance this guy's gonna be, which means the amps are gonna go, you know, I'll just go through there. I don't wanna go through you anymore. So it's a little tricky relationship, but that's the reason. Yeah.
So if you put a load between the third prong of the potentiometer and ground, maybe third or I'm not sure, second, yeah, that one.
Okay.
And that, a load between there and ground, you'd burn out the potentiometer, right? But then you'd have a really high amp draw through the.
No, actually, because the potentiometer, by the time you go all the way through this thing, is quite high resistance. So there is actually the slightest current going to ground there. If there wasn't, if you were to wire it in like that, and some people would say, if you were to wire it like a rheostat, I'm like, well, it is a rheostat, it's just we turn it into a potentiometer and we add a ground to the end. If you were to wire it like this, our transistor will start doing funny things, because now when I point my needle, let's say at the middle, and I'm expecting 6 volts, there's not a slow bleed off down the other end, and just the way they react, funny things can happen where like doesn't open it all the way or it bounces around. And that's a little bit deeper level in electronics we want to go to, but if I remember right, it gets to where it gets hard to shut the load off. Anyway, there's weird things that happen if you don't wire it as a potentiometer. So yeah, there's a trickle effect that just slowly bleeds the power through there. Shane?
Can we switch gears to push the test real quick? Okay.
Not real quick. I'm gonna see if anybody's got a question, because we're gonna go to that next.
Okay.
Amanda?
Can you explain the purpose of the instrument? Like, I don't really understand.
Yeah, when you're flying at night, you wanna be able to see how fast you're going.
Is it
And if
just
there's no
one-
light bulb to shine on the airspeed indicator, you have no idea how fast you're going.
So it's literally just like one.
Could be wired above your head, could be wired as an eyebrow light in the instrument, could be wired onto the dashboard and shine on multiple. So
We
what,
only use one.
you only need one on your board, but yeah, it might be one light bulb, it might be 10 light bulbs. Oops. Slideshow. In this old aircraft, it's probably just a light bulb up here somewhere that shines on everything,
Okay.
if you had instruments. And this aircraft, each one of those has its own light, and we're just gonna wire them all in parallel. All right. Very good, so yeah, instrument light, you might say instrument lights, if you wanna put it that way. All right, now we'll shift gears. Oh, yes?
Alright, this is kind of relating to the ignition circuit.
Nope, not yet. Sorry, go, I'll say go for it, but
Sorry, not the ignition, the starter circuit.
starter circuit, okay?
So, it's normally open switch.
That's the ignition circuit again.
No, it's the starter. You want an intermittent normally open switch.
We'll cover that in the lecture today. Hold that thought, if I don't answer it, we'll come back to it. All right, Shane, we finally made it to the push to test. Good questions, just hold the thought, because that's today's PowerPoint. So, push to test button. Who was it? David that was talking to Dean, and they redrew the inside of it, I think. So the FAA likes to draw them with a goofy arrow inside. So there'll be your push to test. You have a light bulb inside there, right? And they'll draw it, and I'm even helping. But there's your terminals. There's your 3 terminals on the thing. They'll draw it like that, and the arrow just, it messes with me. If you see one drawn with an arrow like that, this switch still is the part that flips back and forth when you push the button for the push to test. The arrow is supposed to tell you it's like a momentary or it's a push to test. It's a terrible way to draw it. But you'll see it that way on most of the wiring diagrams and FAA stuff. So when you see it that way, you kind of know what's going on. So what we did, I should have just drawn the other one that way too. I should have drawn these bigger. So Dean kind of corrected us, and it makes it easier to see what's going on. If we draw it really big like this, and give us our 3 terminals, that might be visually more appealing to help you understand what's going on the inside. So normally the power's coming through here, through the light bulb, and out. And when I push the push to test, that guy shifts up. And now I would have to have power coming through here to power the light bulb. So I drew one of each drawing down here with our landing light. So I now have 2 push to tests on my landing light, which works just fine, right? Still does the thing. So circuit breaker, switch for the landing light. I could put that in a little bit of a box if you want it. So that's my normal switch to turn my landing light on and off. So if the landing light is off, I do not have power going through the landing light, and I can't get through the push to test lights because of the way the contacts are. But as soon as I turn my landing light switch on, now my landing light has power going through it. And electricity can go backwards through that switch, through the little light in the push to test, and illuminate your push to test button. Same here on this one. It goes through the contacts, through the light, and does the push to test button, okay? If I were to open that back up, yeah, something like that. On this one, if I push the push to test over, now I'm connected to that other set of contacts, so the power will come through the push to test, through the light bulb. And the important part on that is it opened the circuit to landing light, right? So I will light up my push to test, but because that switch moves it, it doesn't light up the landing light. If you wire this wrong with the 3 terminals, you might get it to kind of work. But we've had people, I don't have it drawn out right now, we've had people wire them in so when you do the push to test, the landing light comes on with it, and you go, something's not wired right there. So that's how that works, and it'd be the same thing down here, right? If I push the push to test, the electricity can come through the little switch in the push test, through the light, but it won't go to the landing light. I'm almost there, Marcy. So if I have it set normally, and I close my landing light switch, so I got power going to my landing light, I would have power back feeding to those push to test lights. If I push on the little light bulb, the little setup, what's going to happen is as I'm pushing, I'm going to go halfway with the switch first, right? Because it's not like immediately all the way there. When I'm halfway, my push to test light's going to turn off because it's not connected to either of them. And then when I finally finish pushing it all the way, then my push to test light will come on. So that's another way that when you're done with your project, I'll kind of test to make sure you got it wired right, because I don't necessarily trace all the wires. I look at your wiring diagram and assume that's how you hooked it up. So I'll go to the push to test light, I'll make sure it's off, I close this, and then both come on. and then I'll slowly push the push to test, and I'll see your push to test light bulb go off, and then back on when I come back over. So that's how those work. You can hook those up, like we said, a bunch of different ways on micro switches for gear, all kinds of crazy stuff. We're just doing it on probably the simplest method on this one for, hey, am I sending power back beyond this? Okay, Marcy.
So you're saying that if you have the landing light switch closed, you don't want the push to test light on.
No, if the landing light is closed, the push to test will be on
Okay.
because the power is going through the normally closed set of contacts that the push to test has. I think I just drew that wrong. There.
Okay. And then if it's open, sorry, if it's open, then the landing light won't be on, but if you press the push to test, the light will be on. And then you said if it's closed, and then you slowly press the button, it turns off for a second, and then it comes back on.
Yep. So there. I just drew it to the really big one. Cool? Okay. So right now with the switch open, my push to test, oh, I draw that backwards? Oh. Switch those two. This one's the one that's normally on. There, that's better. So, with the light off normally, I'm not powering the light bulb, but if I were to push the push to test, it's gonna turn the light bulb on back through this wire. Yeah. If I close this, then I got it powered, so, yep, exactly. All right, moving on. Yep, that's what we're gonna do. Oh man, it's already 10:02. Tell you what, you guys want a little break 'cause it's Friday? Okay, let's make it just a 6-minute break. So come on back at 5:02. We'll just it'll be more like a stretch, grab a coffee 'cause it's a Friday. I'll get the PowerPoint going.
Quick question.
Yeah.
That's not time.
Yeah, so, kind of an ugly drawing, ugly drawing on the bottom of this side. So if we compared that to, say, everybody else's drawings and stuff, you'd be like, whoa, there's some room for improvement here, right?
I thought it was like a
Yep.
sketch of how it was an official. I just wanted to know, I didn't see any more.
Yeah, exactly. Yeah, that's basically what it is. Yep. But you still got what, 98?
Yeah, no, it's fine, I just didn't know what,
That's definitely 98 level, almost 100, but there's some room for improvement.
They hit it just right, like,
we'll do the other one better.
Well, yeah, that one should be way better, it's a whole grade. Yeah.
Oh, that's right, it's a whole lap.
Yeah.
Yeah.
The other camera.
Okay.
Does this help you if I get out like this a little bit? Or not at all?
No, it's not really.
Okay, I'll talk about it. It's like 10 times more people about
Well, I did draw it out. I didn't put in where we needed to do.
So then how,
Except I didn't put in.
yeah, I need a blinker
And
for
the light
the-
needs to be on the left side.
I didn't really. Okay.
Well, I guess it can be on the right side.
Is it always on the right? See, this is why I can't draw it, because I don't know anything about
I don't
You
know.
gotta be more careful with your I don't know anything statements. We don't know anything about planes. Did you pass general?
I don't know yet.
Did you pass any of the classes in general? You know a thing or two about planes then. Or was that Marcy? That's Marcy. Oh, see, I've been talking to Marcy. She gives me the same line. I don't know anything about this. I'm like, you don't know anything about this? Come on, I wasted my life for the last 2 months. You know a thing or two.
Think about yourself when you first got here, and how much you know now.
Yeah,
You might not know everything, but you know so much more.
yeah,
Yeah, I didn't mean it as like a, oh, I don't know anything.
Yeah,
It's
yeah.
just like a, learning comment, but.
yeah. No, I totally get what you're saying. And I'm trying to build you up. You guys are doing a lot better than you think. In the flight program, it's way more frustrating than this program because as soon as you get like halfway decent at something, we move on and we start something you're terrible at again. That's kind of the point of the program over there. So all year long, you're like, I'm so terrible at this. I don't know what I'm doing. And it's because, well, as soon as you get it, let's do something you don't know how to do at all.
Flight trains, if it was in this program, you would have us be doing work on airplanes already. You'd be like, I don't know what I'm doing, 'cause I'm expected to do it already.
Yeah, and when you get about a 70%, we'd say, let's move on. You're like, I don't know how to do it yet. You're like, close enough, we'll finish it later.
See, that would drive me insane. Actually, that does drive me insane.
I thought I was having to lower my lower my standards for this already, you know?
This class.
Yeah, like, I feel
Yeah.
like when I get to about a 90.
Yeah,
it's
the
like,
blue one out there?
oh,
Yes, my wife bought floor mats, I took some tanning off, it's not bad. I think if it lasts, the interesting part's the smell. I'm not sure if it's actually the valve cover leaking oil onto my exhaust anymore. I'm actually wondering if it's the cheap exhaust fix I did, it's still just getting too hot and making a burning smell. Cause it's getting less and less, so.
Maybe you're just getting used to it.
Yeah, no, I think, I was gonna buy one of those air fresheners, but no, it's a decent car.
Maybe you won't your tongue?
But I was
I
wondering
could
if
leave the
it's
school and
Friday,
say, this is the
last
concept
day
of
or-
it. Don't ask me how it works.
Yeah, yesterday, the last day.
so they're going to quarters.
I just need
Oh,
those two
yeah.
letters.
So I was wondering if you can release those
Do that
2 minutes
AMC.
early.
Give 'em extra time for this afternoon. Yeah, we can do that. What's a few minutes mean?
10, 15 minutes.
Alright, will do. Nice. Oh, Moodle wasn't working this morning. I can't get on Moodle. I don't know if it's the network here that's not working, or if it's
So
Moodle.
Yeah, try it again. 'Cause
I'm
internet-
getting, that, the network was down.
Okay,
And that's like the first thing I see in the morning is with
alright. I'm gonna go jump in my office. Well, I can do it here. I don't know my login is. Thank you. I showed up an hour and a half early because I couldn't, I don't know what the deal was. Couldn't sleep. Yeah, well, the weather changed, I think. I woke up with a slight headache and I was like, I'm getting old.
It's a lot.
Weather changes and I can't sleep all day.
Feeling it in your knees yet?
It's not a yet, that's a, I don't know that I feel the weather in my knees, but, yeah, when I wake up, it's, when I go to put my socks on in the morning, my knees creak.
Okay, so you ever had jet lag, but then when you go to get jet lag, it's like, wake up super early.
Yes, sir.
Super good. It's like the opposite of what you'd
Yeah,
expect.
actually,
It's a weird feeling.
Yes, because
that's a big one. That shouldn't have any lights. I put that on top,
Okay.
because that's miscellaneous, all kinds of goodies.
There's two big ones. There's multiple big ones. So there's one more big one underneath.
I pulled one up, my back is telling me about it.
That's what I was wondering, is if when stuff got disassembled, if it didn't, I don't know.
I don't know, it used to be in the parts on the shelf.
Oh, yeah, no.
It's gone.
Sure, going to see.
Can you guys open the?
Send your kid there.
Alright, I'm gonna make sure you can open it, because you might want it. It opened yesterday. Something happened between yesterday and yeah. You guys get into today's. There it is. Alright, I'm gonna try one more thing. Sorry, I want you guys to make sure you can have it. Alright, nobody's in a hurry. We'll just deal with it after this. Alright, let's get going. Can somebody try to open PowerPoint 7 for me? Yeah, should be what I'm showing you now. That one good to go? Okay. It's got something to do with if I change it in PowerPoint, but not open it on Google, sometimes it works and sometimes it doesn't for you guys. So I gotta go back into my G drive and open up all the PowerPoints. It's a hassle. Okay, we're back though. How do you make the word one disappear? Add a G to the beginning and then it's gone. Some of you are struggling with that one. That's a good one. Alright, it's Friday. I got good news. I have some of the best news. Really, it's the best news ever. Believe me, my people, I have the best people working for me. And I work with the best people. Nick said since it's Friday and we're done with general, that I can give you guys extra time to go to Culver's. So, not saying you have to go to Culver's, just saying I'm going to Culver's. So we'll dismiss at, I don't know, 1:45 today, something like that, so you have plenty of time to head out, which means cleanup time should really start at 35 after, to make sure you're cleaned up, especially because it's the weekend, and we got, you know, and you are welcome to leave all your stuff out on your workstation, right? That's how it works, over the weekend or whatever. You don't want a terrible messy workstation, but with all these wiring stuff, it happens. Just don't leave them out on the rest of the table. All right, ignition switches. Yeah, this is gonna be fun. So we're gonna go way old school. Have you guys seen this airplane yet?
Is this in the,
It's actually, those don't look like our cars. That might not be our airplane. I thought it was though. Anyway, pretty old airplane. Who can find the ignition switch? Anybody?
Is it two switches?
Left switch.
Right here. Those are the magneto switches. So you got left mag, right mag. They're just a switch, and they will ground out the ignition. So I gotta pause for a second. Whoops, wrong one. I wanna take a volunteer. I was gonna do it with a spark plug, but it's too hard to wire it really quick. So you guys, I assume, kind of have a basic understanding of spark plugs. How we've got one electrode going through the middle, and then the outside's the shell. If I put like 20,000 volts difference between those two wires, I'm gonna have a spark jump from one to the other. So that's how a spark plug works. If you didn't know that, welcome to SMAT. We'll teach you nothing to work on airplanes by the end of the year. So if I had a spark plug, and I wanted to say don't spark anymore, one thing I could do is send a monkey into the airplane and have them put a little wire from the leads to each other, and I'm not gonna get a spark anymore, right? Because why would electricity want to jump through that big resistance air gap if it can just run through the wire? So that's one way to do it. How many of you have worked on a super old engine where they got the spark plug wire going to the top of the spark plug, and the way to kill the engine is they just have a piece of metal dangling above it, and you just push that metal down onto the top of the spark plug. You seen one of those?
Wasn't on a super old engine, it was actually on a pretty new, wood chipper.
Interesting, yeah. So basically all they do is the same thing I said, you just don't send a monkey inside the engine, you do it where the connections are outside. You just ground out the lead, so what's trying to make a spark just goes through that little wire. Now, our electricity class, you'd be like, aren't you making a direct short? And when we do ignition class, you'll find out it's not that big of a deal, because these are not making a lot of amperage. They make a lot of voltage, not a lot of amperage, so it doesn't hurt it. In reality, when we get to that class, there's a coil, it's a step-up transformer, it's like 1,000 to 1,000 windings, I think. So it's like 1,000 to 1 windings in this thing. So if I put in 240 volts, I'm gonna get out 24,000 volts. That's kind of the idea of what a coil is in a magneto. So on these, we actually short out the, let's call it the 240 volt side, and make it not spark. So that's what your ignition switches are connected to. You're basically doing the same thing. You're just shorting it out so that the spark says, I don't want to jump that air gap. I'll just go through the short that you're making. We just do it on the low voltage side of the coil instead of the high voltage side. So I was going to do it with this one and be like, if I hold these apart, this scared me. If I hold these apart, I get a spark, right? Because the voltage gets so high it jumps. If I hold these together, no spark. And look, I can touch both leads and it's not shocking me. Because why would the electricity want to go through me when it's just going through the wires to each other, right? Is that making sense for everybody? All right, so that's exactly what we do with our ignition switches. So when the switch is open, the spark's gonna say, I gotta go somewhere, and it's gonna jump the spark plug gap and make your engine run. When you close the switch, it basically says, well, I'm not jumping that spark plug gap anymore, I'm just gonna go through you, Mr. Switch. So, when you have it closed, or that would be the off position, and you say, I don't want my engine to run, you technically have an amp draw that's running through the switch, right? Because every time the spark plug would want to spark, instead of jumping through the spark plug, it goes, well, I'll just go through that switch instead. It's much easier. Everybody follow me so far? All right, so if we had a wire break, from our ignition switch out to our magneto out to the engine. If the wire's broken, that's gonna act like an open switch. It's gonna act like we're saying, go ahead and run, Mr. Engine. So that's one of the reasons when we get to power plant and whatnot, we're gonna inspect really close to make sure that we don't have any broken wires. That's why as pilots, after you get done flying, if you're a good pilot, you'll take your switch and you'll roll it over to the off position and you'll make sure your engine basically sputters and it's gonna die. You're making sure you don't have any broken wires going to this thing. After you flew, you say, yup, I can turn both magnetos off, and then you turn them back on and get going. The reason you do that is if the wires were broke and you just turn the aircraft off with the fuel or other methods, and later on somebody's turning the prop around and we get some gas in there, if it's a broken wire, that would be like having the switch in the on position. And as you turn the prop forward, you could potentially cause a spark and have it go boom. And people have been killed that way before, I think. They've been hit pretty bad for sure. So, that's why we want to be careful and why they're reverse acting of what we would normally think of when we think of switches. Alright, so old school, it was just a switch. When the switch is closed, it grounds out that system. Here is a slightly updated version. And out here we've got ignition left, ignition right, so same situation. Right now I think those are turned off. Typically our switches, and we cover this in power plant, but I'll give you a little preview. Our switches are down when they're off, they're up when they're on. Same thing, forward is on, backwards is off if you're in the cockpit. The way I remember that is if you had an air conditioner outside and you got that big old disconnect that's like a boom, and that turns the power off, and boom, and that turns the power back on. If you were to fall off a ladder and land on it, you don't want to land on it with the wires flopping around and shock yourself. So it sounds silly, but if you fall off a ladder onto the switch, you want it to turn itself off. So same thing applies in airplanes. So these switches, those are all off and off, but technically off means the switch is closed on those two. That's kind of ironic. That's interesting, right? So those switches would be mounted kind of upside down if you want to phrase it that way. So there's the ignition switches on that one. And then we get a little newer yet. Here's the Citabria from SMAT 5052 Golf. Me and Kurt got a few hours in that one, don't we, Kurt? It's a fun little airplane to fly. Mission switches on that one are up behind your head. They're not even on the panel because they're on a thing that looks similar to this. They're actually this type of switch. But you got a left switch on off and a right switch on off. And you start the aircraft with this little button here that says start. So that is the switch that goes to the starter motor. So when you go to start the Citabria, you're going to reach above your head, you're going to turn both magnetos on, which actually means you open the switches to them, so they're not shorted, right? So you turn both switches on, and then you push this, you hold that button down. So that is a momentary switch. It's only closed, it's only connected while you're holding it. So we call that a momentary switch. So in your projects when we say we want you to put a momentary switch in there, the idea is we're simulating when you push it, you're running the starter for your engine. A lot of you guys, well some of you guys are trying to figure out to where you can like run a fan blade to something and you're like, oh yeah, when I throw it to start I want the fan to stay running. And I'm like, well the problem is in an airplane the reason it stays running is after you hold the starter for a minute, all of a sudden we have gasoline going bang, 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 and it's turning the prop. We're not running our propeller on electricity, right? That would be, well, I mean, some planes do that, but not us. So if you're trying to figure out how do I wire the prop that turns when I push the start button to stay running when the mags are in the both position, we did come up with some ideas, but it's quite complicated. So if you're interested in complicated wiring diagrams and a little bit of a challenge, I gave one to David, it's kind of fun, but we're not going to cover it with all you because we'd probably start losing you with what we're doing. But if you want to figure it out later, you can come to me. So here's some other ones. You got ignition left, right, and the start button. That's kind of cool, right? Okay, thank you. I didn't know if you were having so much fun with ignition switches as me that you just wanted to watch the lecture. I told him it's one of my favorite ones all year. Oh, did I see a hand?
Yeah, so I'm sorry. If you said that like usually when you pull like throttle and make your back, it's off, and that's with most things in the aircraft. But isn't that the opposite for our heat? You pull it on.
Switches, electrical switches. Down is off, up is on, forward is on, back is off for electrical switches.
Okay.
Controls, that rule doesn't apply for it.
That's what I was.
Yeah, no, that's for electrical switches. All right, slightly newer, all right, here's one off a real old airplane. Basically what they did is they said, you know what, this is too much work for the pilots. They're lazy. They don't want to have to turn 2 switches. They only like to turn 1 switch. So the guy came up with this one, which we have a couple of these old versions here. I absolutely love looking through these. It's part of the, wow, that's so cool. I can't believe they figured out how to do that. So we got a bunch of different styles where you got off, right, left, both. And that's basically how these are set up. So with this switch, we're still going to need a start button, right? But they put these 2 switches in here. So if I have this in the off position, I'm going to have basically this set up here, and I've got ground connected to, it's a terrible drawing, but it's connected to there and there. So in the off position, and when they draw these, they'll give you 2 arrows because if you notice, we're kind of moving 2 sets of switches in here. So that's how they try to draw it. So if I'm in the off position, we'll make, so this is my right magneto, that's my left magneto. So in the off position, both my right magneto is grounded and my left magneto is grounded, because off means close the switch to ground, right? All right, so if I were to move this down to the L position, and notice the dotted line, so if I move 1, they both move. If I move that down to the L position, what we're saying is I want to run on my left magneto only. So if I move it to L, my left, whoa, I drew that backwards. Sorry. I want to run on my left magneto only. So my left magneto is now not grounded anymore. Notice that terminal just goes nowhere in space. So the left magneto is not grounded, so the spark will go through the spark plug because it can't come through the switch. But the right magneto, the spark can come through the switch, and that means that the right magneto is not going to spark into the engine because it'll just go through the switch instead. So that's when I'm set in the L position. If I set it to the R position, and you'll notice they only label one of those for you, but you could transfer them down here, off, L, R, both, because the arrows are moving together. So in the R position, the R wire just goes to the middle of nowhere, which means it's open, which means the spark plug's going to have to be sparking. But the left mag is now connected to ground, so the left mag won't work. If I go all the way to both, now both magnetos are just going to a point in space, not connected to anything, which means both of them will be sparking at the spark plugs because we have not grounded either of them out. Pretty cool? Amanda?
Why would you want to only have 1 magneto?
It would be for testing. So when I go to fly, I want to make sure both my magnetos are working, and there's really not a good way to do that. So I'll start the airplane on both, and I'll switch this over to just the left mag, and the engine will still run, but a little bit not as good. So I'll go to left, and I'll go from, let's say, 1800 RPM, and it'll run at 1700, because it runs a little bit better with both magnetos on. So I'll do that, it'll go to 1700, I'll go back to both, up to 1800, and then I'll go to right, and that tells me that both my magnetos are working. Then I'll go back to both. Now, if I was on both, and let's say the left magneto wasn't working, something's busted with the left magneto. If I switch it to left, basically I turned the right one off, right, or grounded it. Now my engine's gonna go, it's gonna die. So if I go to left and my engine dies, that tells me, ooh, my left mag is not working because I shut my right magneto off. So that's the answer to that. Yeah.
That
Oh, sorry, not you. I was over top of your head. We'll come back to you though. You both started talking.
Isn't there a case where the engine died in the air and we find that one of the magnetos was killing it, so you just went left on the other?
I've heard that theory. I've never had that happen. I don't understand why it would,
I don't
but
know, it's just on the checklist.
it's on the checklist. I think what it is if your mag were to rotate to an advanced position, it could fire the cylinders too early and start this funky detonation thing. And then basically when the correct timing is there, we already lit it off and it's not. So it's a really weird if one of the mags was to actually spin and start firing 20% early. And that, I've never had it happen, but it's potentially a thing, but crazy rare, yeah. Grant.
Do we need to use that diagram in our electrical schematic?
This is a great one to use, and that's a great question. If in your wiring schematic, you just draw a switch for me, and you say ignition right, that will work. But we're going to draw a diagram. If not on one of these slides, I'll do it later, and I'll show you how I would draw it and how I would wire it. Because this one's a little bit more complicated. So it would be best if you did this, and when I say best, it helps us understand what you got going. But I understand what's going on, and most aircrafts won't draw this out. We use this in school setting. We don't usually use it in the drawings because I don't know, it uses too much ink or something. So good question. Takes up a lot of space on the page. Amanda.
Why do they stop at 2 magnetos?
We have, well, it's one engine. So we have 2 magnetos so that if one magneto dies, we don't fall out of the sky. So they say, let's put 2 sets of spark plugs on our engine. So we have 2 sets of spark plugs, 2 magnetos, so if one system dies, the airplane still flies.
So 1 magneto is only powering half of the spectrum?
Yep, there's top spark plugs on your cylinder, and each cylinder has 2 spark plugs. So one magneto will power one of them, the other magneto will power the other. Yep. So the airplane still runs with just one magneto, just not quite as good. Unless you have fancy magnetos, like the Sureflies we'll learn about later. That actually runs pretty good on just that Surefly. But anyway, that's another story. Marcy.
The bottom magneto in the diagram, it goes off, right, left, both.
Off, left, right, both. It's going to be the exact same.
The top and the bottom are going to be the exact same?
Yep, and it's because this little dotted line says those 2 pointers are connected. So this is the L position, that's the R position, that's the both position. It's the same on both of them. So let's see, we'll review. This wire will be on the back of our switch, L. This wire on the back of the switch will be R. It'll go to the left magneto or the right magneto. Yep. Okay. All right. So on your board, I'll admit last year when I drew this, I did a much more complicated drawing. And then some of you guys, well not some of you guys, some of last year guys wired them up. I was like, well that's way more simple than what I was trying to do. Because I was trying to figure out how do I send positive voltage through this and hook like a positive voltage up to the ground terminal. And I was like, well that's way more complicated than I gotta be. So here's your bus on your board. Positive voltage, right? So there's our positive bus. So the simplest way to hook this up is give yourself a little light bulb, whether it's an LED with a resistor or whatnot, and I guess that means we need a circuit breaker, right? Circuit breaker, light bulb, and then we're going to come into our ignition switch. You can draw it like that if you want, but if you would like, I don't know why I drew it from the left side, it was just fun. So this will be our left mag. This will be our right mag. And we'll take them off the same one just for the fun of it. And we'll call this the left. And this the right. And then we'll go out the ground. Okay, so I did not necessarily connect those with a dotted line and draw all 4 positions because we're going to make the assumption that you know this is an ignition switch. So on your drawing, if you just do it that way, I'm okay with that. The understanding would be if I have both switches this way, which position is my magneto switch in? James? Am I on off, left, right, or both?
You're on off.
I'm on both. Because they're open, they're not grounded, which means in an airplane, both magnetos would be sparking at the spark plugs, right? Not shorted through. So the issue here is if I want both of those light bulbs to be lit up, I would have to do that. Now what position am I in, Geese? Off. Now I'm in the off position, that's correct. So if you wire it this way, you're going to want to put a little label next to your thing that says right mag off, left mag off, to tell you that when the light bulb is lit up, the mag is off. Now that's kind of, it's not as fun, right? Because it's fun to have where when the mag's on, the light bulb's on, because that kind of like, oh, my engine's running, right? So if you want to do it a little fancier, what you can do is instead of a light bulb, you can make that the coil. It's a bad coil, but you can make that the coil in a contact that would have a normally closed set of contacts, and then that would go to a light bulb that would then go to ground. So if it's a normally closed contact in like one of those little black boxes, now when I have this set to off is what we said, right, is our current position. If it's off, this will get energized, which means it was normally closed, but I opened the contacts. I did that backwards. I said that backwards. Ah! We want it on the... No, I said that right. Hold the phone. Hold the phone. I want, when this is in the off position, oh, that's why. I want it to be, we'll go this way for the explanation. I want it to be on both. When it's on both, I want this to be, yeah, normally closed. I said it backwards because I was looking at it when there wasn't electricity. Let me back that up. Oh, wait. So, it is a normally closed contact. And just a FYI, if you got a contactor, they'll usually have a drawing on it, like that. And there's 2 terminals. Maybe this is 30, maybe one of them is 87A, and the other one's 87. Maybe. It all depends on the manufacturer. And then you might have like a 86 and an 85, just maybe. Maybe I should have changed the numbers so they were different, but that's, I think, what the little black one looks like, right? So, these go to the coil, and those are the contacts. So what we have here is, I had to put a jumper wire between 86 to 30. Yeah, so that's where we're at. So, if this is unenergized, the coil's not energized, we're in the normally closed, and my light bulb is on. So that way, if you're in the both setting, our light bulb would be turned on. But if I turn it to the off setting, now my coil goes click, and it'll switch the contact points, right? And now my light bulb won't be getting power anymore. So, you can wire it like this if you want. Your light bulb, you'll just have to label it as left mag off, right mag off, or you can add one more contact to your thing and you have the light bulbs light up when you would normally say my engine's running. Okay. Good. Let me erase that. need help with that, go talk to Dean. No, just kidding. You can come to me, talk to Dean, do whatever, watch the video. I think I even have it on your next slide down there. So if you want to go in your own time, I've got it down here. That's one other way to do that, which is sometimes on a wiring diagram. You guys might not be able to see that drawing, so I'll draw it a little bigger. You guys see that drawing? There, I'll do it that way. On a wiring diagram, notice I have R2 labeling the coil on there. That's telling me that's relay 2, the coil for relay 2. Sometimes we don't draw the contacts to relay 2 right next to the coil for relay 2. It's somewhere else in the page. And that's what I have going on here. So on this one I have R2 contacts there. Now technically, if I wanted it to be the light bulb, I'd want that to be like that on the normally closed is what we said, right? So sometimes that happens on our drawings so that we can move the contacts into a different frame. And the reason we do that sometimes is we might be controlling a 12-volt system with our coil that is going to then turn on and off a 400-volt system that is 400 volts somewhere else, if you will. So we'll have it on a different page in the wiring diagram. All right, we're going to step from old school up to modern, basically what we have on most our switches. Because what they did is they said, hey, these are pretty cool, but I'm still too lazy. Turning the mags to both and then moving my hand to the start button's too much work for us lazy pilots. So they want to be able to just take their key and go all the way to start and let go and have the engine start because they're really lazy. So that's why we get these. So inside here is this. So we went from just 2 switches, right and left. We added a start switch, and this LR and the BO, we're just going to ignore for now. By the end of the year, you'll have to understand what's going on there. That's with a shower of sparks, and it's a whole different ignition system. That's in power plant class. So you can pretty much ignore what's going on with some of that drawing. But what I want to highlight for you is inside this ignition switch, you've got your left switch, you've got your right switch, and then you've got a start switch. So if we put power into the BAT terminal on here, you'll notice it only connects it to the S, to the start, which would go out to our starter contactor. It only connects it to the S when we're in this bottom position. So instead of relabeling all these and wasting a bunch of ink, it's the same situation. You see the dotted line where we can come up here. The bottom position is the start position. So if I'm in off, if I'm in right, if I'm in left, if I'm on both, I'm not going to have my starter energized. So the only time the starter is energized is when I'm all the way over in that start position. Making sense? Question?
For the sake of simplicity, we can assume that the left start position is also grounded, sort of like the LR thing.
Just ignore LR. You're not going to use those 2 terminals. So,
Right, but on the right mag switch, the start position is grounded.
so on the mag switch, if I go down to start, you'll notice that is grounded. So good observation. That is only true if this jumper right here is installed on the back of your switch. And here's where I just geek out. I'm like, I can't believe I know this. This is so fun. So, what I just circled, that they didn't look very optional, is a jumper. Oh, it's hard to see up here. It is a jumper between these 2 terminals. So this one is R, and this one is not labeled very well, and that's why I kind of geek out, because it took me a while to figure this out. But this is basically a GR terminal, ground. So if I put a little jumper plate between those 2, that's this jumper plate. And then when I go to the start position, my right magneto will also be grounded out. If that little plate is not installed on there, if I were to open this. Then, when I'm in the start position, both mags are open, which means they will both fire. So, great question. It's actually my next slide. I couldn't even wait to hit the button. So, this is the paperwork. It lives in the mag box. If you get a chance, it's really fun to read through this. We don't necessarily go this deep or review it in power plant class. We kind of do because it's a ways from now. We'll talk more about the magnetos in power plant class, assuming you retained all this information I'm giving you right now. So, if you get a chance at the end of class, this is a great little read, and it basically talks about, see where it says jumper, used when left mag is retard mag or impulse coupler. Basically what they're saying is if your right magneto shouldn't start it because we've got a retard contact on our left mag or impulse only on the left, not on the right. So you got to know what they're talking about here. But basically they're saying if you don't want your right mag to be starting your engine because we somehow delayed or delayed the left one, install that little jumper. And when you look at these and you look at the back of them, it's hard to read the terminals, but those are the only two that are basically right next to each other with the flat plates pointing the same way. You could not put a little plate that size on any two other terminals, right? They purposely put them there so that you can install that little plate on there. So, kind of fun thing to read and get familiar with. When you guys put your engines on aircraft in power plant class, you may be swapping mags around, and you'll watch really close, and we'll teach you about what retarded timing is and stuff like that. But you got to make sure that if you have two impulse couplers on your aircraft, you don't want that on there. If you only have one impulse coupler, you do want it on. We had like 3 groups last year that did not have their mag switch wired correctly because engines are coming off and going back on, and they just weren't paying attention, I guess you'd say, and putting what we're learning now into power plant class.
If there's only one impulse coupler, you won't really on the left.
Yep.
Is that why?
Yep, we will, I think without exception, if we turn one of the mags off at the start, we'll always turn the right mag off at the start. Yep, so we always start the engine on only the left mag if we're only starting on one mag. Yep. I can't think of any exceptions to that rule.
Is that pretty common to have just one, or is it?
Used to be, wow, something weird. Used to be, once they came out with these switches, it was very common. The idea was impulse couplers could be higher maintenance and blah, 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 so we don't want them on both our magnetos. So they're like, well, we only want to put it on one magneto, we'll put it on the left one, we'll just shut the right mag off while we start the engine. All right, there we go, we're back. We're not going to take that one. We're going to go kind of fast through it. What I do want to do on that with the paperwork, we have a bag that's got a handful of these that are disassembled. The switches inside here are not quite so, where's the one you can see? They're not quite so straightforward as just this rotary switch where you can follow the contacts. If you get a chance, it's kind of fun on the ones you can follow the contacts to follow the wires. So this is the ground wire, you can see they go through here, and you can be like, okay, so if I'm off, neither my right mag nor my left mag are connected to ground. You can kind of, no, they're both connected to ground, sorry. If it's off, they're both connected to ground. So you can look through and see that. This one's similar. This is actually off a DC3, possibly. So this has the left engine mag switch. So on the left engine, you got both left, right, off. The right engine, both left, right, off. And because the pilots are so lazy, I tell you what, these pilots, they're terrible lazy. They are too lazy to even move both switches. So they also have just shut them all off. Because the actual reason for that is on old ones, they'd set them to both, my understanding, I've never flown one, they'd set them to both with the mags off, and they'd start cranking, that would get the oil and some fuel in the engine, and then they kick the mags on to get the start going. So that's technically why it's there. It's because while you're cranking, you don't want to have to be switching all of them. But I like telling the story the other way. So that's that one. Look through those. Oh, point being, so these ones, take a look at the ones that are disconnected. The bottom plate here, plastic, basically just has a whole bunch of terminals in the rotation as you go around. And then the housing has like 3 little brass or copper pieces. And depending on what position you're in, will depend on which overlap they're connected to. So it's definitely a little bit more, I'm gonna use the word advanced puzzle to try to be like, oh, I don't understand how that's working. But this is a ACS bulletin. You can take these apart if you have the proper info. If you have a switch that's bad, and you can replace the little contact points and stuff. So if you get a chance, they're kind of fun to look through. All right. Yeah, we're gonna keep going along. So wire shielding, we're gonna rip through this pretty quick. Remember, when we're set to, especially the off position and they're grounded, we're sending electricity through here. But even if we're in the both position and they're not grounded, there is a little bit of a capacitance where it's like static electricity, where that spark plug, it's like, I want to go through that switch. Even though it's open, you get a little bit of a bounce of electrons back and forth, because it's 24,000 volts, right? Or, well, 240 on the one end. That bouncing of electrons would send a signal out to our radios, and you'd hear on your radio. It's not good. Sometimes it's more of a staticky, but you'll tend to hear it if it was a problem. So what we did is we take our wire that goes to our ignition system and we wrap it with steel so that that's a bad picture, it's the reverse. We wrap it with either steel or copper, usually it's copper, so that those electron signals, the magnetic flux, don't go out into space and interact with our radios, they just go through it. So we call that a shielded cable. This one is designed to say, if I have a shielded cable, outside influences can't get into my cable, because they're just gonna hit the shield and go around and continue on. So it does 2 things. It both keeps outside influences from getting into the cable, but in the instance of a ignition cable, we're trying to get the inside influence. We don't want it to leave. So either way, it's a locked door, if you will, for magnetic flux lines. So how do we make those connections? Here's a picture on the back of a ignition switch. It's got this one connected to, I'm gonna go the right, because here's the plate that would be flat across. So the middle wire connects to the right, and then the shield will bunch all up and solder up, and we wanna ground that out. So the shield is going to be this black wire that runs back into the G terminal that's grounded out here. So that's how we ground it. So here's the picture. I did this in front of class the other year, and it took forever. You couldn't see, so I just gave you some pictures. This particular one actually has 2 conductors on the inside. It's pretty rare. I don't think we have this wire around anymore. So in an instance where you have 2 conductors on the inside, we do what we call cap and stow. We'll just take a cap, it's pretty much just a crimp, like a wire nut, but we don't use wire nuts in aviation, right? Crimp it on the end of the wire, and we're gonna tie it up and we're gonna get rid of it. If you ever cut a wire in an aircraft, and it's just dangling, you're not gonna leave the wire dangling. You're gonna cap it, and you're gonna stow it. So that's a side point for today. Cap and stow is, you got a wire going nowhere, put a cap on the end of it, and get rid of it so it doesn't go find something to touch. So, ignore the blue wire because we capped and stowed it. So, what we're going to do is we're going to solder an additional wire onto there. And then we're going to bend our additional wire backwards, put it under the heat shield, and that additional wire was the shielding that'll get connected to ground. So, how do I pull my wires out of there in the first place? Oh, here's just some more images. The Aztec, one of the test stands out there, if you want to look at it, it's got a version of this, so if you lose the piece that I'm passing around right now, that we probably already passed around, you can go look at that and be like, how do I do that again? Oh yeah, Here's the magneto side, because the other side of the wire is going to be similar. So the middle wire is connected to what we call the P lead. You'll learn about later on the magneto. The ground wire that got connected to an additional wire, so the shielding comes around and connects. Now, if this was an actual functioning aircraft, I would take some lacing and then lace it to it, so I don't have a big floppy piece. But this was for informational purposes. All right, so you're going to first strip off the outside insulation. Now I'm looking at the shielding. I'm going to take and bunch up the braid, kind of like a Chinese finger trap, loosening it. I'm going to take a little prick, and I'm going to get myself a hole in the braid. Once I have the hole in the braid, I'll make the hole bigger and bigger and bigger until I can pull the inside wire through that hole in the braid. Now I'm pulled all the way through, I got the braid, I'm going to solder a wire to it. So I got the wire hanging out, and after I solder the wire to it, I'm going to put some heat shrink over that solder connection, and now I've got my ground connection and my main wire connection. Making sense? What we don't want to do is this. I pulled this off and online. They called it pesky P-leads. In a minute, the manual will say, well, sometimes the manuals don't tell you how to do it. Now, the Cessna 172 will absolutely give you an image of something very similar to this. They'll say that's how you do it. Older aircraft, they might not have told you. They were like, do it however you want. So on some of these old aircraft, they would have taken just the ground shielding, hooked it up to a terminal, and hook that up to ground. Well, the issue is this isn't insulated, and we fly the plane, that thing's bouncing around in there, and all of a sudden it starts grounding out our mags, and the mag's working, then the mag's not working, then the mag's working, then it's not. So that's why we will cut that, solder a wire to it, put it under a heat shield, and then run the wire out separately. We do not want to do this, even though it would look like it works. They can bounce around and hit stuff we don't want them to touch. Joe? Okay. All right, last thing before break. Shielded wire is what we're dealing with these. Technically, shielded is not coax. Coax is coaxial cable, meaning I've got a conductor and I've got one conductor on the middle and I've got a second conductor on the outside, kind of like if you're using your shield as a ground wire, it's a second conductor. Coaxial would mean if I was to draw a circle, let's make this bigger. Here's my middle wire, and here's my outside wire. If I was to pick a point that I said, what's the middle magnetically if I run electricity that way through it for using my hand rule for my magnetic lines, the middle of this one for using the hand rule is right there. The middle of this one, has the same access point. So that's why we call it coaxial cable. So magnetically, they have the exact same magnetic center of flux point. So the issue with a coaxial cable is if I dent it, if I dent the outside, now I just moved the axis for that outside one over a little bit. Now the axis for the outside one, I'll switch colors. We'll do it this way. Inside conductor still has its middle there. Outside has its middle there. Now I don't have the exact same point, the same access, and if this is a communications line, that can mess with our communications because the way the magnetic fields interact with each other. So, what we do not want to do with coaxial cable is bend it too sharp, because if we bend it too sharp, it could move that inside conductor inside the insulation. We don't want to step on it, because if we step on it, we can damage the outside one. We don't want to drop stuff on it. Oh, there it is. What I missed? Kink, drop, step on, bend it too sharply, loop it too tight, don't pull it, because if you stretch it, you can bend it and mess it up, and don't use it for a handle. But the idea is we want to keep it coax. So technically, our ignition leads are shielded, not coax, because these want that wire you have there. It's not a coax where it's whatever. So, all right. last slide, I didn't know which one to put this in, so I just added it here. I was like, this is gonna come up later in the year, and I'll be like, oh, I already taught you that. So switch derating, I don't care about this for your projects, but you need to know about it. If you have a lamp, and we talked about this briefly before, but when you turn the lamp on, the amp draws really high until the light bulb gets hot. Remember that lab you guys did in general? Where if you measure the ohms on the lamp, it's not very much, and then you turn it on, and you have much lower amp draw. So, with a lamp, if you have a 28 volt system, if you have a switch, you need to derate your switch by a factor of 8. So if that switch normally says, hey, I can take a 10 amp load once this lamp is going, you're gonna say, okay, if you can take a 10 amp load, let me multiply that by 80%. Now you can only take a 2 amp load, or divide it by 8, multiply by 80%, same thing, right? Is that, actually, I'm not sure my math is right there. Double check. 10 divided by, yeah. No, 1.25. So you multiply, let's read it. Find the nominal rating of a switch pair to operate a device, multiply the continuous current rating of the device by the derating factor. I gotta go to the other side of it. You're mathing it up. So, if I multiply the continuous of the device, okay, so if I have a lamp that is, let's call it 2 amps, the way the chart works is if it's a lamp in a 28 volt system, I'm gonna take my 2 amps times 8, and I'm gonna need a 16 amp rated switch. So even though I'm only running 2 amps through the switch, once it's established, my switch contact points have to be rated at 16 amps in order not to burn up. Notice we have 28 volt and we have 12 volt. So if they ever ask a question, don't just get too lazy. If they say it's a 12 volt system with a motor and your motor draws 10 amps when it's running, what does your switch have to be rated at? So if I have I'm going to write this up because I just tried to trick you. I have a 12 volt system with a motor that runs at 10 amps. What does my switch need to be rated at? 20. 12 volt, so it's not that one. That one. So it's a 2, not a 3. We'll try to trick you on purpose. So I'm going to take my 10 amps times 2, so my switch needs to be rated at 20 amp switch. So make sure you're on the right voltage on the chart because they're a little different. It's kind of a weird thing. All right. That's there. It might come up later. I don't care on your projects, but in an actual aircraft that counts. Now, the last piece of that is a relay. A relay, or a solenoid contactor. This is considered a remote switch. It's remotely operated. You control the little coil in the cockpit, but the relay contacts are considered a switch. So this applies to your relay contacts, okay? So that applies to your relay contacts. So you gotta size your relay contacts according to that chart. I'm assuming it's still 11.4, and it switched the number on me to AC43. All right, that's it. Questions, comments? Good. Kept it under 2 hours. Perfectly. 10 minutes short. We got 10 minutes early today. Dismissed.